Hey guys, so this is my Python code for the B1 assignment for Dr. Jimmy Lawrence and for 3102. So let's get into it. All right, so the problem statement concerns a brick wall with a thickness of 0.5 meters. It's initially at room temperature of 300 degrees Kelvin, and we were asked to determine the time for the center temperature to reach 425 degrees Kelvin, and the left and the right wall sides of the wall were respectively 425 and 600 degrees Kelvin. Let's get into it. So I started with an Excel file. As you can see here, I said that the T0, T1 are my intervals, like going through the length of the wall in 1D, one dimension, just the X direction. And I named the center to be T5, which is why it's highlighted. So the steps were to the right under the DT column, and I found that 425 was reached after or between 23 and 24th iterations, which I interpolated in a second. So we'll go ahead and get that. So the stability criteria that I used was labeled as dt is less than or equal to 1/2 times delta x squared divided by alpha. And I used alpha given, dx was 0.5, and I calculated the delta t using the stability criteria for a one-dimensional surface. I interpolated the value to be between 23.4, or to be 23.4, and the delta t I switched into hours after computing it in seconds, and then just multiplied the delta t times the iterations to get 17.2 hours as my final answer. So using the equation above on this slide, we're going to plug that into code. This is my code, so I started out really simple, and I just imported the numpy and the plotting, the matplotlib. I also made initializations, so I said alpha, and then the t left and t right of the wall were 425 and 600. The t, which is what I'm going to be changing in my loop, is going to be 300 degrees Kelvin, and the t plus and t minus are also going to be 300 degrees initially. The seconds I'm going to start with are 0, and the tx is going to be 0.25, and the delta t, the time step, is going to be 1. I made a few arrays just because that's how it made sense to me. So the little t array is for the time, and the big T array is for the temperature. So I'm going to call on those later in the loop as well. So the T left array is going to be pulling the left side of where we are in the value, and the T right array is going to be pulling the right temperature of that value. So if we go on and look on the right side of this presentation, we're going to go into the while loop. So I said while t is less than 425, and I once again initialized the t left and t right to be 425 and 600, and then entered the t left array as the initialization and the t right array as the t right initialization as well. I set new criteria for t minus and t plus, which just was pulling the next value of the previously set arrays, which is how it's going to go into the loop. And then I appended the t minus and t plus values, which just means I added those onto the list in the array in order to grab those values to plot them later. So for the overall t, the center, I calculated it to be the equation that was shown before, so alpha times dt divided by dx squared times t minus 1 plus t plus 1 plus 1 minus 2 times alpha times dt divided by dx squared times the temperature, the previous temp. So this t value, this time value, is just adding on 1 second in the loop so that it keeps looping, and it keeps adding time going throughout the wall, and keeps going and calculating. So these last appendages or these last append functions are just adding on the temperature calculated and the time calculated to those arrays and adding them in a list so that I can plot it later. The time is divided by 3600 in order to get it into hours. So we're going to go ahead and look at the graph. All right, so this is the graph temperature change I did print the time that it took the center of the wall to get to 425 degrees Kelvin is, and then the number I got is 16.318 hours. And then I just simply graphed a temperature versus time plot very simply. So that's it. That's my code. Thank you all so much. All right, for part C of the question for assignment B1, we were asked about the stability criteria predictions. So for one-dimensional, it's only in the x. That's why it's 1 over 2, because you're taking the x that you want and you're going 1 before and 1 after that x. For 2 and 3 dimension, it's the same thing, except you're doing it for 2 dimension for the x and the y, and for 3 dimension for x, y, and z. Therefore, you just have double and triple for the 2 and 3 dimension before and afters. So that's why it's 1/4 for 2-dimensional, is because you're taking the before and after for both x and y, and then for the 3-dimensional, you're taking the before and after for x, y, and z, which is why it's 1 over 6. So thank you all so much. That's my presentation.